Good morning, everyone. So myself, I am Krishna Chaitanya. So I'll be dealing. I would like to discuss power semiconductor drives. So till now, we have studied about different types of motors, maybe DC motors and AC motors, and we have studied their construction, operation, and their speed control and all. But coming to power semiconductor drives, so look at the name of the course itself, drives. There is a specific course on a motor. There will be a more number of research areas in the motors. So why much so much focus on the motors itself? Why much there is so much concern about the motors itself? So if you take a average domestic load, so 90% of the load in an average domestic house will be motor itself. You may take the washing machine, you may take a ceiling fan, a pump used for the water used for the pump, and maybe air conditioner, a mixer grinder, everything. So 90% of the loads used in the average household application will be motor load. So 90% will be motor load, and remaining 10% will be a light load. Light load may be a very low value of low power required for electronic loads. Electronic load which needs actually very low power. So since 90% of the the power what is being fed to a domestic load is motor load, so if you save more amount of power over here, so we can save more amount of power on the generation side. Coming to, if you take industrial application, so again 90% of industrial application load depends upon motor load again. So industry itself indicates something has to be rotated. So a commercial building needs a motor load, consists of motor load, air conditioners, fans and all. So nothing will be there except light and air conditioners and fans. So if you take any sort of type of load, 90% of the energy generated, I can say 90% of energy generated is solely used by the motor load. So if we operate the motors more efficiently, so it could say that if you operate the motors more efficiently, you could say that the power will be saved. So that the power saved at the generation side. So if you save 1 kilowatt of power over here, it may save more than 1 kilowatt power from the generator side, because the power has to be flow from generator, transmission network, so many number of transformers and all until it reaches the end point or customer. So the every component the power encounters will have some amount of loss. So if you save the power over here, 1 kilowatt of power over here, obviously more amount of power will be saved from the generation side. So the sole purpose of this course is to operate the drive more efficiently. So the word, I could say, whenever they say the word operate the drive or control the drive more efficiently, what does it mean actually? So controlling the drive itself indicates controlling the speed of the drive as and when the load is demanded, as per the load is demanded. So how can we control the speed of the drive? So conventional or in traditional cases, we have so many methods to control the speed of the drive. So just like a ceiling fan has to be control the speed, so we have a conventional way of regulators where the voltage will be controlled linearly by using a resistor. The power will be wasted in the form of the form of a heat in the resistor. But later, the speed of a ceiling fan can be controlled using a electronic regulator. So the conventional way of controlling the voltage or controlling the speed of a motor will be expensive, bulky. If you observe the speed control of a ceiling fan, the regulator will be look like this and it will be mounted over the wall. But the advent of electronic switches, power semiconductor switches, the speed control of the same ceiling fan will be made use of a small regulator which can be installed inside the wall. So this will generate the heat, that's why it was installed outside the wall. This will not generate the heat because it was inside the wall. So obviously we can say that the conventional way or traditional way of controlling the speed of motors will be very expensive. I can say we can have another example of controlling the induction motor using a dimmer or auto transformer. So a laboratory motor of 50 or 20 kilowatt or 1 HP or 3 kilowatt or 5 kilowatt, generally it needs a dimmer of around very bulky maybe some 8 amperes or 16 amperes of capacity. So whereas the cost or weight of the conventional thermostat will be pretty high, which leads to expensive method of speed control. So coming to with the advent of power electronics in 1970s, so the so-called conventional way of speed control become obsolete, and then the power electronic semiconductor switches has become more popular, and they made it very easy for controlling and more efficient in controlling the speed of the drives. So the title indicates the control of motors, whether it may be DC or AC, using semiconductor switches of power electronics, which are of power level. Power level indicates that a voltage and current level or power level will be pretty high. So a power level semiconductor switches which are used for controlling the drives of the DC or AC drives indicates the course titled power semiconductor drives. So what are different types of drives? We have DC drives and AC drives. So how to control DC drive using the so-called power electronic converters? So we have to control DC drive, we need variable DC, we need variable DC. So what are the different converters that can give you variable DC? So we have two types of converters. One will be a rectifier whose input is AC, and one will be chopper, that is a DC to DC converter, which will give you again variable DC, but whose input is fixed DC. Whose input is fixed DC. So to get the fixed DC, again we have to convert AC to DC using a rectifier. So either we can have a chopper or rectifier to control DC motors. How about AC motors? How about AC motors? We have AC motors need three phase variable voltage and variable frequency supply, and this can be our inverter. But how can be inverter will be fed? Inverter can be fed with DC. Since we don't have DC readily available, we need to connect rectifier for converting AC to DC. So this may include both induction and synchronous motor. So using the so-called inverters, we can control both AC and DC motor. We can control both induction and synchronous motors. Using rectifier and choppers, we can control DC motors. So the major advantage of using power electronic or power semiconductor switches and power converters using power electronic switches is the loss incurred in these power converters will be pretty low, because they can operate at very high efficient, because every power electronic switch will have zero loss, ideally zero loss across it when it is turned on or off. We do have some switching loss. We can have many number of methods to avoid the switching loss. So the loss incurred in the power semiconductor power converters is pretty low. So we have a more efficient operation of the DC drive. So we can supply as much amount of power required per the motor itself. We cannot waste the power in any other component or passive components, just like the conventional way of controlling the DC and AC motors. So the controlling our drives using the so-called power converters is pretty advantageous and more efficient in nature. So every motor load system is derived from a basic torque equation, so called, I can call it as a fundamental torque equation, which was given by T equal to TL plus J d omega by dt. So if a motor, if a load needs some 20 or 50 Newton meters of power, mechanical power. So if a motor needs 50 Newton meters of mechanical power, this is load which needs 50 Newton meters of mechanical power, and such a load is connected to a motor who can give 50 Newton meters. So will you think the problem is solved? The load needs 50 Newton meters. Do you think the problem is solved? The load needs 50 Newton meters and I am supplying 50 Newton meters through my motor. Obviously not, because every load which is at rest or at static, if you start rotating the motor, obviously it needs more amount of torque than it actually needs, because everything which is at rest will have a certain moment of inertia. Because of that inertia, to make it in the motion, to rotate in a particular speed, I need to supply more amount of torque than it actually needs, and that torque will be dynamic in nature. That means the torque, the torque which is needed by your motor, which is needed by your load, additionally will depends upon the change in speed only. Whenever the speed changes, obviously more amount of torque will be needed. Just like a cylindrical structure, iron structure, when we try to move it, so initially we need to push it with using more amount of torque. Once it is in the running condition, the amount of force or torque we are applying on it will be reduced, because at the starting position, since it is at rest, so the load has to overcome its inertia. So we need to give more push than actually what it is required when it is in motion. So that torque which we are giving more, which we are supplying additionally when it is rest, is called dynamic torque. The name dynamic is given because since that torque exists only when there is a change in the speed. Initially, when the load is at rest, the speed is 0 and we are making it to rotate particular speed. So there exists a change in speed over here, then the dynamic torque sits over there. And once if you want to change the speed again, it is already rotating at a particular speed, and again you want to change its speed to a higher value, again we need to give more amount of push, we need to supply more amount of torque, again the dynamic torque will sit over there. So dynamic torque exists in a particular load system whenever there is a change in speed. But once the speed is settled, I could say the steady state is reached, the dynamic torque will die out. So that is why, since the dynamic torque depends upon the change in speed, we have given the expression d omega by dt. It depends upon the value of change in speed, d omega by dt. Omega is the speed, angular speed, with d omega by dt is the angular speed, change in angular speed with respect to time. But what is J here? Because every load doesn't have the same amount of inertia. Maybe a bicycle will have very less amount of weight, it offers very low inertia when you move. An iron cylinder or a heavy bike or a vehicle will have more amount of inertia when you move out it into the direction, a particular direction. So it depends upon the weight of the motor, weight of the load, it offers more moment of inertia, different moment of inertia, and will have a different amount of dynamic torque. So dynamic torque also depends on, it not only depends on the change in speed with respect to time, it also depends on moment of inertia, or the inertia it offers with respect to its own weight. That is why J is also added. So I could say J d omega by dt is nothing but J d omega by dt is nothing but the dynamic torque. The dynamic torque, every load will demand whenever there is a change in speed, and TL is load torque, the torque actually required by the load, and T is motor torque. T is motor torque, the torque supplied by the motor. So our motor has to supply more amount of torque than the load is actually demanding. So we need to supply, my motor has to supply two torques now to the motor. One is the torque actually needed by the motor load, second one is the dynamic torque because of the moment of inertia. So looks like the J, the moment of the polar moment of inertia, it look like a culprit because it is demanding more amount of torque than actually required by the load. But in some cases of load, this moment of inertia might help the motor itself, just like in some applications where the load is intermittent in nature. The load might appear at one moment and it might disappear the next moment. The load again might appear in the next moment, it might disappear in another moment. Such type of load can be a drilling machine. So if you connect a drill bit and if you try to punch a hole or make a hole or the wall, so the moment you start drilling the hole, the load will be appeared. You are loading the motor. So within few seconds, the load will disappear if you take the drill machine out of the wall. So in such cases of drilling machines, such case of applications, so whenever you try to make a hole or you try to load the drilling machine, the motor inside the drilling machine, the d omega by dt will become negative. Why d omega by dt is becoming negative? Whenever you try to punch a hole or the wall, the speed will fall down. Whenever speed falls down, d omega by dt, the change in speed will get reduced. Speed will get reduced. If speed is getting reduced, d omega by dt become negative. So whenever d omega by dt become negative, the so-called expression, fundamental torque expression, T is equal to TL minus d omega m by dt, it become negative. The so-called expression will become T equal to TL minus d omega m by dt. So I could say that T plus d omega m by dt is equal to TL. So what happened now? The same dynamic torque is now added to the motor torque. It is aiding the motor torque to serve the demand torque required by the load, TL. In that case, the moment of inertia or the dynamic torque stored in the drilling machine will be helping your motor torque to drive the load. So in this case, if the load requires some 50 Newton meters, if this load requires some 50 Newton meters, you need not take a motor who is having 50, who can produce 50 Newton meters, because the dynamic torque of the machine itself is helping you. So you can take a motor that can give you 30 Newton meters. Remaining 20 Newton meters can be supplied by your dynamic torque. So you can have a motor of very small size, a torque of value less than the demand torque by the load, so that the machine can have, the motor can be easily equipped inside the drilling machine, so it can be handy, easy to carry and all. So depends upon the type of application, this moment of inertia will act in such a direction. So every analysis of the drives, whether it may be DC drives or AC drives, whether it is controlled by rectifiers or choppers or inverters, this fundamental torque expression will comes into picture, and the analysis will be made with the help of this fundamental torque expression. And one more important point of analysis in power semiconductor drives is all the power semiconductor drive analysis will be made using power converters in steady state. No transient analysis will be made. Let us see the block diagram of an electric drive, how an electric drive actually look like. So we do have motor over here. Let us take a AC motor who needs variable three-phase AC, variable three-phase AC. So since ours is a power controlled device using power modulator, so the three-phase variable AC is being supplied by a power modulator, an inverter in this case. So this is the input to the power modulator, three-phase AC, fixed AC, maybe fixed, and this power modulator will be given the input by control circuit. And we have a speed detector, maybe a sensor which always senses and measures the value of the speed of the motor, and the value of speed is being fed as input to our control circuit. And we have another input to the control circuit given by speed reference. So if you look at the block diagram, we have a motor and a power modulator. So obviously power modulator converts the fixed AC to variable AC, fine, so the motor is happy. But how about having the power modulator input? The power modulator needs to be told when the switches are to be turned on, when the switches are to be turned off. That can only be supplied, that can only be controlled using the control circuit, who is responsible for supplying the firing pulses to all the switches of power converter. So the control circuit will supply the required firing pulses, the much needed firing pulses for the power converter. But how can a control circuit supplies firing pulses? So it has need to be controlled again, and it has need to be supplied with a particular input. So the control circuit will have an input of speed reference. So this is the reference of speed what we are giving as an input to the control circuit, and the control circuit is also having the current speed of the motor, which is supplied from a speed detector or a sensor, a sensing unit I could say. So this control circuit keeps on checks between the reference speed and the current speed of the machine. If once, let us say the machine is rotating at some 1000 rpm and I have entered some 1200 rpm over here. So the error 200 rpm will be processed by the control circuit. So correspondingly the firing pulses will be increased or decreased based upon the error signal or polarity of the error signal, and this will this will decide the amount of firing pulses. The firing pulses will be fed to the power modulator switches, and then accordingly based upon the pattern of the switching and the value of the switching pulses, obviously power module will operate and the output voltage will be varied. So called the motor will be supplied with a different power, I mean to say increased voltage or decreased voltage. Obviously the speed will be increased. This process will be continued until the error becomes zero. I mean to say the current speed of the motor detected by the speed regulator reaches the speed reference what I have entered over here. So I could say this is the block diagram of an electric drive. So electric drive basically consists of a motor, and actually we have this motor is connected to a load through a shaft. So basically electric drive consists of a motor load system with a power input from the power modulator, which is controlled through firing pulses from a control circuit and much needed sensing unit. So out of all the power components of the electric drive, the power modulator is the most sensitive part in the system, because the power level of the sensing unit and the control circuit, entire thing, so the power level of the control sensing unit and the control circuit, this entire thing will be much lower value, much lower level, maybe a few volts, few amperes. But how about the power level of motor and the power converter? Several hundred amperes, depends upon the size of the motor, size of the amount of the load we need to supply. So several hundred amperes of current has to be carried through your power electronic switches and the motor. Motor is basically, especially AC motors, are much rugged in nature. They are robust in nature. They could carry 3 to 4 times of high full load, their rated current for a few cycles. They could bear such amount of high current, but the power semiconductor switches inside the power converter cannot handle such amount of high current even for a few cycles. So the most sensitive part of the entire block power electric drive is the power converter. So we should be very careful while operating the system, since the power converter is expensive when compared to the control circuit. So obviously we need to be more careful in controlling the machine. So controlling a DC motor, with single phase full converter. We can also control the same DC motor with single phase half converter. We can also control the DC motor with DC to DC converter. So which one gives you more advantageous thing? So coming to full converter and half converter. So full converter and half converter. Semi-converter can give you only one polarity of the voltage. I mean to say voltage cannot be reversed if you operate the firing angle of the semi-converter. Whereas in case of full converter, semiconductor can give you only one polarity of voltage and one direction of current. Whereas in case of full converter, the polarity of voltage can be reversed, but not the direction. So since the voltage can be reversed but not the direction, I can control the motor in terms of two quadrants. The voltage applied can be reversed. We can change the operation of the drive if you use single phase full converter. If you use single phase semi-converter, the mode of operation of the motor cannot be changed. If it is operated in forward conduction mode, you can only operate it in forward conduction mode forever. So by using single phase full converter, you can operate it in two modes of operation can be possible. But using a DC to DC converter or dual converter, it is possible to control the motor in 4 modes. That is, we can run the motor in one direction, we can brake the motor in the same direction, you can run the motor in reverse direction, you can brake the motor in reverse direction. That is, a 4 mode operation of the motor is possible. So we need that kind of motor, we need that kind of drive controller, we need that kind of power converter where we can control the drive in 4 modes of operation. 4 modes of operation. Let us see what are the 4 modes of operation. If you see the 4 modes, this is first mode where I can say it is forward motoring. That means torque is positive, speed is positive. I could say motor is, this is the direction of motor torque, this is the direction of motor speed. Forward motoring. This is second quadrant, this is quadrant 1, this is second quadrant where torque became negative but speed is positive. Speed is positive but torque is negative. When can we need the developed torque to be negative? When the load needs to be stalled, when the load needs to be stopped. That means whenever we want to apply the brake on the load. So applying a brake on the load can be done easily and efficiently within less response time, can be done using developing a negative torque inside the motor. So torque has to be negative, and since the motor is rotating in the forward direction, the speed will be slowly reduced to 0 and will become stalled. So this can be called as forward braking, forward braking. And coming to the third quadrant, torque is negative, speed is negative. I mean to say, torque is developed in this direction, torque is developed in this direction, speed is also rotating in this direction. I mean to say, motor is rotating in reverse direction, torque is also developed in the same direction. So I could say this is reverse motor. So write the written notes and submit as an assignment of all the things what we have discussed about the block diagram of the motor and the fundamental torque expression. Thank you.